Hello everyone, I am Amir Didehkhorshid from College and University. In this video, I'm going to present our paper titled Selection Performance Using a Scaled Virtual Stylus Cursor in VR, where we explain and evaluate a tablet and stylus-based interaction technique we developed for VR systems called Warped Virtual Surfaces, or WVS for short. But first, a bit of background. Supporting input techniques with haptic feedback for VR interaction is challenging. Most of the available VR platforms use 3D track controllers for input. They borrow designs from game controllers. There are two high-level approaches to haptics. One, get a physical prop and track it in 3D. The prop can either be exactly the same shape as a virtual object or some approximation of its shape. Two, use devices like the Phantom that provide force feedback. As we know, neither of these approaches is the perfect solution. They either get too expensive or require a lot of equipment and cumbersome setup to work properly. One of the earliest approaches used to support haptic feedback in past research was to use planar surfaces or tablet-like devices for input. Different interaction techniques were developed using tablet-like devices with either stylus or finger-based input, and they were proven to be quite useful. To give a few examples, techniques like IVR Note use tablet-like devices to allow users to take handwritten notes. Or in the case of personal interaction panels for general interaction in 3D environments. Others like Bowman use tablet-based approaches for text entry. More recently, several HCI researchers came up with a somewhat new class of techniques for VR interaction based on visual illusions. The techniques work based on the fact that vision dominates proprioception and vestibular cues in the brain. The most well-known technique used in this sort of approach is perhaps redirected walking. The basic idea behind redirected walking is to go beyond the physical limits of the tracking space and enable real walking in VR. Other techniques like haptic retargeting use a single physical prop and mapped it to multiple virtual ones. They redirected users' hands towards the physical prop as users were reaching for virtual targets. This was achieved through space warping and body warping without users noticing the redirection. This leads to our proposed interaction technique, warped virtual surfaces. We wanted to repurpose fixed-size panels and tablet devices to represent arbitrarily larger virtual panels in VR. As you can see in the figure showing our prototype, we use a tablet tracked using a Vive tracker, and we evaluated performance using Fitts law methodology. Users were shown the blue targets in VR, but they were selecting the orange ones physically with the stylus. To do so, we use scale factors to scale up the virtual panel and introduce warping on the virtual cursor position to compensate for the larger screen in VR. The virtual cursor position is calculated by multiplying a scale factor to the real cursor position on the panel. Similar to Osmanian's work on haptic retargeting, we needed a warping origin. We chose the center of the tablet as both the warping origin and the coordinate system origin for both the virtual and the real cursor. Real cursor coordinates were calculated as a value between -0.5 and +0.5. This means when we point to the center of the tablet, we would get 0, 0, and 0.5, 0.5 for the top right corner. Warping origin at the center of the tablet is the only point that stays in the same location regardless of the scale and the tablet size. This causes the virtual and the real cursor to align at the center as if there is no warping taking place. To summarize, warped virtual surfaces introduces a discrepancy between the virtual cursor shown to the user and where the user is physically pointing. With our current warping technique and the warping origin at the center, this will result in the real cursor to fall behind the virtual cursor. In other words, the virtual cursor users see and use in VR is further ahead of where they are physically pointing on the tablet. This is similar to the effect of applying CD gain on a mouse cursor in desktop setups. This won't be disturbing since users cannot see their physical hand while in HMD VR. For our experiments, we used the HTC Vive VR platform, and for our prototype, we used the XP Star 6 digital drawing tablet. We developed the software using Unity game engine, and we use libUSB to access the tablet data inside the engine. The question we wanted to answer was how far can we increase the scale factor and enlarge the virtual screen panel without impacting user selection performance. Based on Coley's previous work on redirected touch, we hypothesized that performance will be no worse under warp conditions compared to one-to-one mapping, meaning no warping at all. Coley showed that users perform no worse in warping conditions compared to no warping at all through a series of experiments using Fitz's law. In fact, they reported that users had to readapt to the real world after spending some time in VR dealing with the direction and space warping techniques, so we were expecting similar results. We measured performance in terms of throughput, error rate, movement time, and target entry count based as defined in Fitz's law, which we won't explain here in detail for the sake of time. Using Fitz's law's reciprocal tapping task, we conducted a within-subject study with 24 participants, 11 female, aged between 19 to 64, with a mean of 26 and a half. More than half of our participants reported to be first-time VR users. Participants had to go through 8 blocks, each with a different scale factor. They had to complete 10 trials with different index of difficulties or IDs common to Fitz's law studies. And for each trial, they had to successfully select at least 50% of the targets. For more details, please see the paper. To analyze our results, we employed repeated measures ANOVA and non-inferiority testing where repeated measures ANOVA failed to find significant differences. Non-inferiority testing might be less known, so we explain it a bit. To do non-inferiority testing, you need to define an indifference zone. If the mean difference between the two conditions and the one-tailed confidence interval fall inside the indifference zone, you can say that condition 1 is no worse than condition 2. In other words, non-inferiority testing allows you to show that two conditions are statistically the same. In case of throughput, repeated measures ANOVA failed to detect significant differences for different scale factors. Non-inferiority test results, however, indicate that one-to-one mapping is no worse than using scale factors. As you can see in the figure here, TP is relatively constant across scale factors. In Fitz's law, we use effective width to calculate throughput. So we looked at how effective width behaved with different scale factors. As you can see in the figure, higher scale factors resulted in lower effective width, meaning participants were probably missing targets closer to target centers. Another explanation for constant throughput could be that essentially the same muscles were used to perform the task physically. Thus, our hypothesis was proven to be true for throughput. Our analysis failed to find significant differences in case of error rate. As you can see, non-inferiority testing indicates that no condition is worse than one-to-one mapping. Thus, our hypothesis was also proven to be true for error rate. In the case of movement time, we found significant differences, especially for higher scale factors, so our hypothesis failed for movement time. This can be explained by participants slowing down under higher scale factors, since warping caused the virtual cursor to move faster for bigger scale factors. We found similar significant differences in case of target entry count for higher scale factors. This indicates that control was a bit more challenging under higher scale factors. Smaller targets were also reported to be harder to select. Linear relationship between movement time and index of difficulty showed a higher regression value for the scale ID compared to the conventional or the real ID. Last but not least, the device assessment questionnaire showed that overall the device was easy to use and required low physical and mental effort. To summarize, participants liked the idea of warped virtual surfaces and the fact that they were able to use a larger panel in VR. We found that throughput and error rate were more or less constant across different scale factors. However, in terms of movement time and target entry count, we found significant differences, especially for higher scale factors. Our results are in line with Coley's work in redirected touch. Finally, we finish with some applications. We imagine warped virtual surfaces can be used with other tablet-based approaches for VR, or to extend the limited physical tracking space of devices like the Phantom. Other applications could be inner drawing or snappable virtual panels. Thank you for watching this video. You can find a link to the paper in the description box below.